Jai Hind, welcome to class of Communication Engineering. These are the contents of the unit, Fundamentals of Communication Engineering. We are going to talk about the basics of signal representation analysis, EM spectrum, which we have covered in the previous lecture, and elements of communication system, need of modulation. Right, so up till here we have covered elements of communication system. So let's start with the need of modulation for now. So as we start with the topic modulation and its need, we need to understand first of all what is communication, what is modulation, what are the various types of modulation available in communication, and what is the need of it. So I'll give you a brief introduction of what communication and modulation is. Communication is the exchange of information between 2 points, a transmitter and a receiver. And the basic blocks or elements associated with communication includes your information source, where the information is generated, that could be in the form of message, that is text, audio, video, pictures in any form, right? Then it has to go to transmitter, and before transmitter it has to be converted into the desired format. So for that specific purpose, we need some transducer which will convert one form of energy into another. So after information source, we do need a transducer. Transducer will convert it into the desired format. That is, maybe the audio signal will be converted into electrical pulses, right? That is audio signal into electrical signal. And the next element, that is the transmitter. The job of the transmitter will be to perform modulation. It will check the available channel and the input signal, and it will do the desired correction changes in the available signal, so as the available channel can carry my signal, right? Channels of two types, your wireless and wired channel, right? And then comes the receiver, which will undo whatever has happened at transmitter, and finally the intended receiver. So this forms my complete communication system. And the question is, what is the need of modulation in it, and what are the various types of modulation available? We know that modulation is basically a process of altering the characteristics of a high frequency signal with respect to the instantaneous value of my message signal. The high frequency signal is called as the carrier wave, and the low frequency signal, according to which we alter the characteristic of our message signal, that is called as my message signal, right? And after modulation, the resultant wave that we get is called as the modulated wave, right? If I want to classify my modulation, we do have continuous wave modulation and pulse modulation. In continuous wave modulation, we are dealing with the analog signals, right? So in continuous wave modulation, we do have amplitude modulation and angle modulation. We know that basic sinusoid can be represented as right. So for an analog signal, the characteristics of wave include the amplitude and the angle. So whether we can alter the amplitude or the angle. The process when we alter the amplitude of the high frequency carrier signal is called as amplitude modulation, and the process where we alter the angle of the high frequency carrier wave, it is called as angle modulation. It includes my frequency and phase. Right, so I have three kinds of analog modulation, that is amplitude modulation, angle modulation, frequency modulation. We can actually call it as amplitude modulation, frequency modulation, and phase modulation. Now, if I talk about pulse modulation, then we do have digital modulation, pulse digital and pulse analog. In case of pulse digital modulation, we have pulse code modulation, delta modulation, and different variants of pulse code modulation like DPCM, differential pulse code modulation, adaptive delta modulation. And if I talk about the analog pulse modulation, then we have PAM, pulse amplitude modulation, pulse width modulation, and pulse position modulation. Right. So Now, if I want to talk about the digital kind of modulation, digital modulation would include my amplitude shift key, frequency shift key, and phase shift key. These are the broad kind of digital modulation techniques that is to be included in the track, right? So we do have amplitude shift key, frequency shift key, and phase shift key. So this is the broad picture of how I can classify my modulation. If you want to actually see how my amplitude wave, modulated wave looks like, if this is my message signal, which is having low frequency, this is my carrier wave with more number of cycle represented here. This is how my amplitude modulated wave looks like. This is all we have covered in the previous lecture. This was just an overview, right? So this is how my amplitude modulated wave looks like. This is how my frequency modulated wave looks like, right? Now let's talk about the need of modulation. Why do we need to perform modulation in today's world, right? The whole and sole purpose of communication is to exchange information between 2 points. If these 2 points are very close, then without any alteration, the message can be exchanged. And if this communication is ongoing with the help of baseband signal, that is low frequency signal, then there is no need of modulation. But in today's world, considering various kind of applications and we being geographically separated from each other, there's a continuous need of exchanging information to far places. And when we need to exchange information to far places, there should be a mean, there should be a way by which we can exchange information without losing our actual essence of the message, without the message being exhausted in power, exhausted in energy. We have to ensure that my message correctly reaches my destination, right? So here I have enlisted the need of modulation. We know that baseband signals are incompatible for direct transmission for long distances. For such a signal to travel long distances, its strength has to be increased by modulating with a high frequency carrier wave, which doesn't affect the parameters of the modulating signal. So these are few basic needs of performing modulation, that is reducing the size of antenna. One of the very conventional method to increase the range of communication is to install tall towers, right? By installing tall towers, we can increase the range of reception, right? With smaller tower, lesser people can be communicated. With taller towers, the range of communication increases. But there comes a practicality about the height of antenna. So this is one of the basic need of modulation, that is, with reduced antenna height, if you want to make your signal propagate long distance, then modulation is needed. In order to avoid mixing of signals, as we know that modulation is actually frequency shifting. So when we shift a signal to another frequency level, then we are actually uh, helping our signal not to get mixed. In increasing the range of communication, that is for long distance communication, it allows multiplexing of signal, increasing the carrying capacity of the channel. Adjustment in the bandwidth is allowed. Yes, with frequency shifting, it is possible. It improves the quality of reception. Yes, there are lesser power losses and other factors associated. Let's talk about reducing the size of antenna. For effective transmission of signal, we know that height of antenna we usually represent it by h, right? It should be comparable to the wavelength of the signal, right, which is represented by lambda. And the height of the antenna should be at least lambda by 4 in length. This is what we know, right? So that the antenna can sense the variations in the signal properly. Now, the low frequency message signal has a very high value of lambda, which will require a very high antenna, a tall antenna, isn't it? Let us calculate it for ourselves, right? We know that the audio signal has range of 20 to 20 kilohertz. So let's choose just any random signal. Let's consider 10 kilohertz. This falls under my audio signal range, which is 20 to 20 kilohertz. Now, as we know that antenna height is calculated by lambda by 4, or we know that C equals to mu lambda, right? So my velocity for electromagnetic waves, velocity of my light equals to frequency multiplied by lambda. So lambda can be replaced by C by F. So here lambda is replaced by C by F. So if we do calculate it, velocity of light is 3 into 10 to the power 8, 4, and frequency here is 10 kilohertz, 10 into 10 to the power 3. And when we do the calculation, we get that height of the antenna comes out to be 7500 meters, which is 7.5 kilometers. Can we imagine that installing an antenna of the height 7.5 kilometers, which is impractical. It's not possible to install such tall antenna. Now let's forget audio signal. We want to communicate in high frequency, 10 megahertz. What happens in case of 10 megahertz? When we are communicating at 10 megahertz, that is a very high frequency, the antenna height can be reduced to 75 meters, which is practical. We can install an antenna which is 75 meters tall. And we know that the message signal that we want to propagate falls in the lower frequency range. So performing modulation, when we are actually altering the characteristics of a high frequency signal with respect to instantaneous value of the low frequency message signal, on here my data is traveling with this frequency, and this frequency is capable of reaching the destination even with the help of smaller tower, right? So long distance communication can be achieved by taller antennas, but there comes the practicality of height. So we perform modulation so that with smaller antenna height, high frequency signals can be communicated. Actually, low frequency signals with the help of high frequency carrier wave. Right? Hence, we need to modulate the message signal over the high frequency carrier signal so that we can have a practical value for the height of the antenna. Although there has been a contradiction that what is the basic single most important need of modulation. So a few authors, they debate about that increasing the range of communication, whether it should be increasing the range of communication or whether it should be reducing the height of antenna. It should actually be reducing the height of antenna, because long distance communication can be achieved by increasing the height of antenna, but there comes the practicality, right? So reducing the height of antenna is the single most desirable need. Next, avoid mixing of signal. If the baseband sound signals are transmitted without using the modulation by more than one transmitter, then all the signals will be in the same frequency range, isn't it? Most of the communication that we do in today's world using our mobile phone, that is, we are talking to our friends, our family, our relatives, right? We are exchanging audio signal, and audio signal falls in the range of 0 to 20 kilohertz. So imagine the number of users occupying the same frequency band at single point of time. So there is increased chances of interference. Yes, there will be interference. Therefore, all the signals get mixed together and receiver cannot separate them from each other. Why not frequency shift them to other levels, right? And this can be achieved with the help of modulation only, right? Hence, if each baseband sound signal is used to modulate a different carrier, then they will occupy different slots in the frequency domain, right? Now, imagine I have 10 different message signals falling in the range of 1 to 5 kilohertz. If I send them as it is, like baseband signal, there are chances of interference. But when I frequency shift them, this I use 10 megahertz carrier, and this I use like 50 megahertz carrier. For in-between signals, I use different carrier signals with different frequencies, quite separated in the frequency band. Then there are lesser chances of signals getting mixed. Right? So this is one of the prime reasons why we use modulation. Now increasing the range of communication, yes, of course. The frequency of baseband signal is low and the low frequency signals cannot travel long distance. When they are transmitted, they get heavily attenuated, isn't it? From Einstein equation, we know that E equals to mc square or equals to s nu, right? A signal with higher frequency will be having more amount of energy, and a signal with lower frequency will have less amount of energy. Then there are more chances of it getting attenuated in the environment, and by the time it reaches the receiver, it is totally exhausted, isn't it? If you being sitting in front of me, you're able to listen to me. You go 500 meters beyond, I will have to use a loudspeaker. You go 5 kilometers and so, I will have to use a device to communicate, right? And what that device actually does, that is not simply amplifying like a loudspeaker does. That does perform modulation. Our mobile phone, that does perform modulation, isn't it? So increasing the range of communication is one of the important need why we do modulation. The attenuation reduces with increase in frequency of the transmitted signal and they travel long distance. High frequency signals are less attenuated, low frequency signals are more attenuated. The modulation process increases the frequency of the signal to be transmitted. Therefore, it increases the range of communication. It allows multiplexing of signals. Multiplexing is a process in which two or more signals can be transmitted over the same communication channel simultaneously. Why are we considering multiplexing here? Let us talk about any communication system, and two most important resources of any communication system includes bandwidth and power, isn't it? Power and bandwidth are two most important resource of any communication system. There should be a way to increase the usability of the bandwidth. The bandwidth allocated to a particular vendor, to a particular user is fixed. Now, we know that day by day users are increasing. So there is a need to accommodate all the customers within the allocated bandwidth, right? When we need to accommodate all the customers within the allocated bandwidth, there should be a way through which we can accommodate them. So multiplexing is a way. What happens in multiplexing actually? I have single way, and I am not allowing single person to travel via it. I'm allowing multiple people or multiple vehicles to travel simultaneously, isn't it? I have a road which is 12 feet broad. One car can pass at a time. Actually, two cars can pass at a time. So why not pass two cars at a time and utilize the available channel, the road, to its fullest? So multiplexing is that process. This is possible with modulation, because in multiplexing we are using same channel within the allocated time, the same bandwidth. Now those signals should be frequency varied, right? And with modulation we are actually doing frequency shifting, and when we are frequency shifting, it is possible for me to allow them to propagate simultaneously through single channel. The multiplexing allows the same channel to be used by many signals, hence many TV channels can use the same frequency range without getting mixed with each other, or different frequency signals can be transmitted at the same time. It improves the quality of reception. With frequency modulation and the digital communication techniques such as pulse code modulation, the effect of noise is reduced to a great extent. This improves quality of reception. There are several kinds of modulation techniques which are so effective in reducing the effect of noise to them. Okay? So it improves the quality of reception. Amplitude modulation. What is amplitude modulation? As we have discussed in the classification, that it is one of the kind of analog modulation. When a continuous wave goes on continuously without any interval, and it is the baseband message signal which contains the information, this wave has to be modulated. Correct? Now, according to the standard definition, the amplitude of the carrier signal varies in accordance with the instantaneous amplitude of the modulating signal, which means amplitude of the carrier signal contains no information, varies as per the amplitude of the signal containing information at each instant. What do we mean by it? I have a low frequency message signal. I have a very high frequency carrier wave. Right? We are altering the amplitude of this high frequency carrier wave with respect to the instantaneous value of the message signal. When it reaches the peak value, the amplitude reaches the peak value, and when it is at its minimum, and likewise. So I can see that this somehow represents my message signal. When I draw the outer envelope of it, this gives me a representation of the message signal, right? So altering the amplitude of the high frequency carrier's signal with respect to the instantaneous value of the message signal, keeping rest of the things constant. It's called amplitude modulation, right? It's my message signal. This is my carrier wave. This is how it looks like. So this is a double sideband full carrier envelope. Here VM represents the amplitude of the message signal. VC represent amplitude of the carrier. VAM represent amplitude of my modulated wave. And when there is no message signal, the carrier is passing as it is. When there is presence of message signal, the carrier is modulated as per it. If I want to make the time domain representation of it, MT can be represented as AM cos 2 pi FMT. If my message signal is a cos signal, carrier CT can be represented by AC cos 2 pi FCT, which is again a cos signal. Then here my AM and AC are the amplitude. This is the amplitude of the message signal. This is the amplitude of the carrier signal. FM is the frequency of message signal. FC is the frequency of the carrier signal. And my modulated signal can be represented with ST, which is AC plus AM cos 2 pi FMT into cos 2 pi FCT, because this gets added up in the carrier amplitude only. The complete message gets added up in the carrier amplitude, and phase of the carrier remains intact, right? What is modulation index? It defines the depth of modulation, up to what depth my wave has been altered. It is represented by symbol mu or small m and is given as the ratio amplitude or voltage of the message signal divided by voltage or amplitude of the carrier signal. From the previous equation, my amplitude modulated wave can be rewritten as ST equals to AC into 1 plus AM by AC cos 2 pi FCT cos 2 pi FMT cos 2 pi FCT, right? And this parameter is my modulation index. It is equal to the ratio AM and AC. Mathematically, it is a unitless term. Mu can be represented as AM by AC. Another formula for it is mu equals to A max minus A min upon A max plus A min. Now, what is A max and what is A min? From here we could see the maximum amplitude acquired by this. This is A max and this is A min, right? let A max and A min be the maximum and minimum amplitudes of the modulated wave. We'll get the maximum amplitude when A max is AC plus AM and minimum when it is AC minus AM. And A max plus A min can be written as 2AC and A max minus A min can be written as 2AM. So this whole equation AM by AC can be rewritten as A max minus A min upon A max plus A min. So this and this, by these two ways we can represent the modulation index of an amplitude modulated waveform. These are three cases of modulation index. If my modulation index is less than 1, this is called as under modulation. This is the case. For all practical kind of communication, mu is considered to be less than 1. It is usually 0.4, 0.5, 0.6, 0.7 and so on. This is the case of my ideal modulation when A max minus A min and A max plus A min, this ratio gives us 1. This is the case of ideal modulation. This is the ideal condition which we never reach. And this is the case of over modulation when this is under modulation, this is ideal modulation, and this is over modulation. Here, this is not appreciable. This is not preferred. Why? Here we can see there occurs 180-degree phase reversal. After this wave should go like this, but this doesn't happen. This goes like this. So here occurs phase reversal. When is the ratio greater than 1? When this is a higher value, right? When this is a higher value, then my V min is somehow from here it goes to the negative scale, and then this is the case of over modulation, which is not preferred in communication. Right? These are the three cases of modulation. How do we define bandwidth of AM? Bandwidth of any system is maximum frequency minus the minimum frequency, maximum minus minimum. And when we talk about the maximum frequency, we need to first see what is the wave equation for my AM. ST is AC into 1 plus mu cos 2 pi FM cos 2 pi FCT. When I expand it using trigonometric functions, we do get these two frequency, FC plus FM, FC minus FM. Right? When I open bracket, this I get AC cos 2 pi FCT, and with this I get AC into mu cos 2 pi FCT cos 2 pi FMT. Now treat it as A and B. Now I know that cos A cos B is half of cos A plus B plus half of cos A minus B. So this is called as my upper sideband, and this is called as my lower sideband in AM. And when I calculate the bandwidth, that will be F max minus F min. F max is FC plus FM, F min is FC minus FM, and subtracting these two, we do get bandwidth of AM, which is equals to twice of FM. What does FM represents here? FM represents here the maximum frequency content of my message signal. Why do I call maximum frequency content, not just simply message frequency? Because my message signal can be a combination of different messages, right? So the maximum frequency content is considered. Maximum frequency content of message signal. It's in hertz. If I talk about how do I calculate power in AM, I have to see the standard equation of AM. My standard equation of AM is, I get here the carrier part, the upper sideband part, and the lower sideband part. Then the total power is a contribution of carrier, upper sideband, and lower sideband. Right? What is the equation for power? Power is VA RMS square by R. Voltage V square by R. Right? So this is RMS value. If I talk about the maximum value, then this can be rewritten as this, right? So PC can be rewritten as AC by under root 2 whole square by R, which can be rewritten as AC square by 2R, right? AC square by 2R. If I check the upper sideband part, let's see the coefficient of cos. That is the actual amplitude. I have to consider actual amplitude, voltage value. So it should be AC by mu. AC into mu by 2. AC into mu by 2. RMS value, so under root 2 whole square by R. So this comes out to be AC square mu square by 8R. Similarly, for lower sideband, AC square mu square by 8R. So adding all three values, what do we get? AC square by 2R, and using these two, and further solving it, we do get total power equals to AC square by 2R, which can be rewritten as PC, and this is 1 plus mu square by 2. So this is something important that we need to remember and memorize, that total power equals to PT equals to PC into 1 plus mu square by 2. This is calculated in what? Right? So if the modulation index for ideal modulation equals to 1, then the power of AM is equals to 1.5 times the carrier power. So the power required for transmission of AM wave is 1.5 times the carrier power of the perfect modulation. Here lies the need of using different versions of AM. That can be understood in another lecture. Right? These are various examples that can be followed for calculating the transmitter power, carrier power, and so on. These are the references I have used. Thank you.